All right, class. Gonna give some supplementary material to what we talked about concerning gas laws in class. So we've been dealing with we left off on the ideal gas law in class, which states that PV equals nRT. And this gas law, the ideal gas law, can be derived, manipulated to solve for any one of these variables, which we know R is a constant, and T temperature is usually given. So I'm going to go with the example we did in class, which was sulfur, hexafluoride, SF6, is a colorless very unreactive gas. Okay, it says calculate the pressure in atmosphere exerted at 1.82 mole of gas with a volume of 5.43 liters at 69.5 degrees Celsius. Okay, so using this equation, PV nRT equals nRT, we know in the X for us to calculate the pressure, so we need to solve for P. Well, we solve for P, it'll be P, and we're going to divide both sides by V here. There goes P equals nRT over V. Okay, so if we look at that, we say P is what we're looking for. Our number of moles will be what? 1.82 moles. R is the gas constant, which is 0.0821. We'll put our units here, moles, and this would be liters atmosphere per Kelvin mole. Okay, and then we got a temperature, which needs to be converted to Kelvin, so it'll be 273.15 plus 69.5. That gives us 5, 6, 12, 14, 342.65 degrees Kelvin. Okay, and then what else? We got the volume equal 5.43 liters. Okay, so if we plug everything in, P equal to 1.82 mole times R, which is 0.0821 liters atmosphere over mole Kelvin. Okay, and that's gonna be times 342.65 Kelvin over the volume, which is 543 liters. Okay, and let me clear this up some here, and this would be 342.65. Okay. Okay. Now we put that in our calculator. We'll get our units, right? Because we know the liters cancel out, mole cancel out, and Kelvin's gonna cancel out, leaves with atmospheres, which you know pressure is supposed to be in atmosphere. So P is going to equal to 9.42 atmosphere once we put that in our calculator. Okay, so let's say we want to solve for, do another example where the problem states it says calculate calculate the volume in liters occupied by 7.40 grams of ammonia, NH3 ammonia at STP, and that's standard temperature and pressure, which we know is at 0 degrees Celsius at 1 atmosphere. Okay, so if we use the ideal gas law, we want to solve for volume, which is PV equals nRT. Well, we divide both sides by P now, because we want to know, it says calculate the volume. So P gives us V equals nRT divided by P. Okay. Now, so using the same steps, we come over here and we say, well, we're looking for volume. Moles, we don't have moles, but we have grams. Okay. We have standard temperature and pressure, so our temperature is going to be 0 degrees Celsius plus 273.15. So it's going to be 273.15 K. And then our pressure would be 1 atmosphere. Okay, so if we plug this in, for the first step we need to do is convert these grams to moles. Okay, before we can plug this in, put this in the problem. So we got 7.4 grams of NH3 times, well, our relationship between moles and the molecular mass would be moles. 1 mole is equal to the molecular mass of ammonia, so that's 1 mole is equal to the molecular mass of ammonia is 17.03 grams, and this is 1 mole of ammonia as well. So we turn that into a conversion factor. It'll be 1 mole NH3 over 17.03 gram NH3, and equals, where's my calculator? Plug that in. 7.40 divided by 17.03. That gives me 0.43 mole NH3. Okay. So I have this. Now I'm going to try to plug it in right here so you still see the same thing. So volume is equal to, the number of moles is 0.43 mole times, again the gas constant is 0.0821 liters atmosphere over mole Kelvin, okay, times 273.15 Kelvin over the pressure, which is 1. Okay, so the atmosphere is going to cancel out, the Kelvin is going to cancel out, the mole cancel out, leaving with us liters, which volume is always in liters. So we put that in the calculator and we should get 9.74 liters. Okay. Alright, so sometimes we know that when we use the ideal gas law, this is for when basically when conditions between the pressure, volume, and temperature remain constant. But when those do not remain constant, we need to be able to calculate these parameters, and we can derive that formula to a new formula, derive the ideal gas law into a new formula. It states that P1, or that's P initial, V initial, over N1, N initial, moles initial over temp initial is equal to P2 V2 over N2 and T2. Okay, so this is how we solve for the initial and the whatever we want to calculate between the initial pressure and the final pressure, P2. Okay, over gas. These are the final states of the gas. So we're using this. Sometimes some of these may remain unchanged, such as if we have a problem and the moles stay the same in the problem, we simply say that P1 V1 is equal to P2 V2 over, we'll exclude the mole parameter because N1 will equal N2 on both sides, so we'll just exclude and use this problem here, this equation here. For example, we do a problem. It says that a balloon with a volume of 0.55 liters at sea level, which is 1 atmosphere, is allowed to rise to a height of 6.5 km, where the pressure is about 0.40 atmosphere. Assuming temperature stays constant, what is the final volume? Okay, so with this problem we see that the moles has been excluded, so it's not going to change. Oftentimes in your problems the moles will go unchanged, so that's why I excluded here. But this time the temperature also remains constant. As we said, assuming temperature stays constant, so we can exclude these two values. So our equation is going to be P1 V1 is equal to P2 V2. Okay, so using this, now it's just time to plug in what we have. Well, say a balloon with a volume of initial volume of 0.55 liters, so we know V1 is going to be 0.55 liters. Okay, has a pressure of 1 atmosphere, so P1 would be 1 atmosphere. Okay, and then it says the pressure is about 0.40 atmospheres after it rises to this height, so P2 is going to be 0.40 atm, and they ask you to solve for V2. Okay, so we simply plug these in. Well, first let's solve for V2 in the problem. So we simply divide both sides by P2. We know these two cancel, so we're left with V2 is equal to P1 V1 over P2. Okay, so now we simply plug in. V2 is equal to 1 atm, atmosphere, times 0.55 liters over P2, which would be 0.40 atmosphere. And V2 will come out to be 1. No, it's going to be units because we're talking about volume, so it'll come out to be 1.4 liters. Okay? Alright. So, moving right along, let's do another example. Let's exercise this equation one more time. Say, a light bulb. Let's do this example here. Example 2. Well, actually, example 3. Okay. So, a light bulb containing argon at 1.20 atm and 18 degrees Celsius is heated to 85 degrees Celsius at constant volume. Calculate the final pressure in ATM. Alright, so the moles, the initial mole and the final mole is going to be the same. And initial volume says that constant volume is going to be the same as equal V2. So we can exclude those from the formula. So now we can say our initial formula was P1, P initial, V initial, moles initial. T1 is temperature initial, P2, V2, moles N2, T2. Well, volume is going to be the same, so we can remove these, and the moles is going to be the same. So now we have P1 is equal to P2 over T1 and T2. Okay. So now we go back and plug it in. What we got? Well, we say that our P1 is equal to 1.2 atmosphere. We say our P2, we don't know. Alright, so our T1 is going to be 18 plus 273.15. That's going to be 291.15 Kelvin. Our T2 is going to be 85 degrees Celsius, and this is degrees Celsius as well. 85 degrees Celsius, not plus 273.15. Okay, and that's going to give us it's going to give us 291.15 Kelvin. Alright, so it's simple plug in. Alright, once you plug that in, I'm not going to do it this time for you. I'll be able to do it by now. It should be 1.48 ATM. Okay, that's the answer you ought to get once you solve for P2. Solve P2 by T2 times T2. These cancel out, leaving you with T2 times P1 over T1 is equal to P2. Alright, we plug it in. Alright. Okay. So now we should be able to understand how to use the gas equations when temperature, pressure, and volume do not remain constant. If they remain constant, we stick with our ideal gas equation. Alright, moving right along. Now we're going to talk about gas stoichiometry. Alright, gas stoichiometry. If you remember, we use stoichiometry to compare the mole ratio between reactants and products to discover how much products was used, or how much product was formed, or how much reactants was used. For example, if we had 10.7 grams of carbon monoxide react with molecular oxygen to produce CO2. All right. Now, it has a formula of 2 moles of carbon dioxide plus molecular oxygen yields 2 moles of carbon monoxide. Okay. The first thing we also have to do, we want to know how much is this form. Well, we got to put this into moles. So we got 10.7 grams times 1 mole over the molecular mass of carbon monoxide, which is 28.01 grams of CO. And this is moles of CO. Well, that equals 0.382 mole CO2. Well, CO. Okay. Well, we see that the ratio between carbon monoxide and carbon dioxide is 2 to 2. 2 to 2. So that mole ratio is 2 to 2. So therefore, we have 0.382 mole of CO, and we want to know the moles of CO2 times 2 mole CO2 over 2 mole CO. Well, we know it's going to be 1, so therefore it's going to be 0.382 mole of CO. Okay, so we're going to do the same thing, which is what we learned in the past with the gas stoichiometry. Okay, let me go back here. Okay, so let's say we wanted, we know according to Avogadro's law, gas and volume, moles and the volume are the same. Okay, so let's say we want to calculate, let's do this example. It says calculate calculate the volume. Let this straighten out. Calculate the volume of O2 in liters, of course. For a complete combustion of 7.64 liters of acetylene C2H2 measured at the same temp and pressure. Okay. 2C2H2 plus 5O2 yields 4 CO2 gas plus 2H2O. Okay, so our formula. So it asks us to calculate the volume required for the complete combustion. Well, we know that the number of moles, according to Avogadro's law, is directly related to the number of volumes. So from this equation, we know that we have it wants us to calculate the volume of O2 for the complete combustion of 7 point of acetylene CO2 measure. So the ratio between this is 2 and 5. We're talking about molecular oxygen and acetylene. Okay, so we got 7 point. So we're going to know how much of molecular oxygen is needed. So in that case, if we compare, we got 7.64 liters of this. Well, we simply say we got 7.64 liters of, you just say C2H2. Okay, times 5 liters of O2 over 2 liters of C2H2. Okay, so we'll put that in the calculator, and we're gonna get 19.1 liters. Okay, remember, this is just like saying 7.64 moles times the molar ratio between these two to figure out how much would be needed at this amount. Okay, so now we get 19.1 liters of O2. That's how much is needed for the complete combustion of acetylene at 7.64 liters a day. Okay, so it's just simply the same thing we've been doing, stoichiometry. Let's do another problem. Another stoichiometry problem. We're actually gonna do two more. Okay, so it says trying to see how not to have to write all this, but I guess I got to. Sodium azide, and that is sodium azide is used scratch that. I think I can go here. Okay. This is, let's say, 2Na3 solid, and that's sodium azide, yields 2Na solid plus 3N2. Okay, gas. Alright, that's our molecular formula for the decomposition of sodium azide. What they say happens is that sodium azide is used in some automobile airbags. And when the impact of collision triggers the decomposition of sodium azide into sodium and nitrogen gas. So as the nitrogen gas produced quickly inflates the bag between the driver windshield and the dashboard. So that's in that airbag is full of nitrogen gas due to the decomposition. Okay, it says calculate the volume of N2 generated at 80 degrees Celsius and 823 millimeters of mercury by decomposition of 60 grams of sodium azide. Okay. All right. So we're gonna use. So it says calculate the volume of nitrogen gas generated at 80 degrees Celsius. So we got our same temperature and pressure by decomposition of 60 grams. So the first thing we gotta do is convert this 60 grams into moles. That's always the key. Okay. So we want to know the volume. Okay, so we say 60 grams, right? Times 1 mole of sodium azide over how many 60 grams over the molecular weight of sodium azide is 65.02 grams of sodium azide. Okay, that gives us 60 divided by 65.02 up 0.9923 mole sodium azide. Okay. Now we have got our mole. We look back at our formula. Our formula tells that the ratio between sodium azide and nitrogen gas is 2 to 3. So we'll say 0.923 mole of sodium azide times 3 mole N2 over 2 mole of sodium azide, and that's going to give us our mole of nitrogen gas, which would be 0.923 1.38 mole of nitrogen gas. Well, now since we had a standard, since our number of moles and gas in chain, we can use the ideal gas law to figure out the volume. Okay, so we say PV equals nRT. Okay, so to figure out the volume, divide both sides by P. So it gives us V equals nRT over V. P, we plug that in. So now the volume is going to be, that's what we're looking for. It's going to be, the number of moles is, straighten this out, number of moles will be 1.38 mole and 0.082 gas constant, which would be 21 liter atmosphere mole Kelvin times 273. 273 plus 80 degrees Celsius. We can still use 273.15. Okay. Alright. Divided by P. All this divided by P, which would be 823 millimeters of mercury. Well, that's not in the correct unit. So we know that 1 atmosphere is equal to 760 millimeters of mercury. So we do our conversion. So we say 823 millimeter mercury times 1 ATM over 760 millimeter mercury equals so that'd be 1. So we need to scratch this and put it in 1. It'd be 1.08 atmosphere. So 1.08 ATM. Okay. Now we plug that into the calculator. Put that into the calculator and we get a volume equals 36.9 liters. Okay. Now, all right. And we're gonna stop right there. We'll do one more, and I'll explain the last little lesson in class, so the video won't be so long. Okay. So, as a matter of fact, just do that last example in class, and I'll do partial pressures now. That way, at least you'll have an example to go back to when you get ready to study. So partial pressures, you see, on your, in just a second. Okay, partial pressures. We've seen that the total pressure you've seen on your POGO activity, that the total pressure of a mixture of gases is equal to PT, P1, P plus, P2 plus P3, and so forth. Okay. Well, problem is we have to figure out what these partial pressures are to get to this total. And the way we do that is by figuring out the mole fraction. Okay? And the mole fraction expresses the ratio of the number of moles of one component to the number of moles of of all components present. In other words, let's say we had gases. Let's say we had gases A, B, and C. Okay. So we need to find the mole fraction of these to begin to solve what the partial pressure would be. So the mole fraction would be A over A plus B plus C. That's how we'll find out the mole fraction of A. Then let's say we want to find the mole fraction of B. We'll say B over A plus B plus C. And the same thing for C. Okay, this expresses the ratio of moles of one component to the number of moles of all the components' pressure. Okay, so we'll do the same thing for C. We'll find out the individual pressure. We'll put them in this formula. So the partial pressure would be represented, let's say, forget the subscripts A, B, and C. These are new subscripts. This was just an example. So the partial pressure, let's just say A would equal the mole fraction of A, okay, times total pressure. Okay, so this is the mole fraction of a particular component. This would be the total pressure. And this would be that partial pressure. Alright. Now, the partial pressure, again, the partial pressure should equal the number of total pressure. And the mole fraction of each component is going to equal 1. Okay? Say that again, the mole fraction of each component should equal 1. And the partial pressure should always equal the total pressure. So let's do an example. Okay? So, let's see, I'm gonna do one right here. It said a mixture of gases contains 4.46 mole of neon. Okay. It contains neon. It also contains 0.74 mole of argon. Okay. And 2.15 mole of xenon. Okay. Calculate partial pressure if the total pressure is 2.0 atmospheres at a certain temperature. So constant temperature. All right. So remember our formula. This is our formula we're going to use. Okay. And you say A can be I and S can be I. These are the same thing no matter what. Okay. So we're going to do the partial pressure of neon. Okay. So the partial pressure of neon is going to be 4.46 mole neon over all of the components, all of the rest of the gases. Okay, the ratio between the subject and the subject and all of the components. Okay, so that'd be 4.46 mole. That's neon. That's going to abbreviate, plus the mole of 0.74 of argon, plus 2.15 of xenon. All right. So if we do the math for that, we'll come out with the partial pressure being 0.607. That's the partial pressure for neon. Okay, now we plug this partial pressure into this formula. Okay, so we're gonna have our partial pressure, which our mole fraction. I'm sorry. Now we plug in our mole fraction. This is not the partial pressure. This is our mole fraction that we're gonna plug into the partial pressure formula. So the mole fraction would be, using this formula, I'm going to turn to a different page. So the partial pressure for neon, I'm going to put partial pressure NE, is equal to the mole fraction of neon times the total pressure, which was 2, remember? So we got everything we need to figure this out. We calculated this mole fraction would to be 0.607, and our total pressure was 2. So this be times 2 ATM. All right, so put that in the calculator at 0.607 times 2 equal 1.21. So this is equal 1.21 atmosphere. Okay, that pressure right there. So we got to do the same thing for the rest of the components. All right, so let's look at argon, which was 0.74. So let's find out the mole fraction. So the mole fraction was 0.74 mole over 4.46 plus 0.74 plus 2.15. Right? And that'll give us that'll give us 0.10. Okay, 0.1. So that's the mole fraction. So now we got the partial pressure of argon is equal to the mole fraction of argon times the total pressure, which would be 0.10 times, 0.10 times total pressure, 2.0 ATM. And that'll give us 0.20 ATM. So we do the same thing for the last one, which would be xenon. So we got find out the mole fraction. Alright. And that'll give us 0.293. Okay, now we plug into our formula, which would be xenon is equal to 0.293 times 2.0 atmosphere, and that gives us 0.586. So now we calculate the total pressures. The partial pressures. Now, the partial pressures, remember we had 1.21 ATM for neon. Alright, plus we had 0.20 ATM, and that was for ATM, and that was for argon. And then we had xenon, which was 0.586 ATM, and that was for xenon. Now this should equal the total pressure. Remember, PT is equal to P1, P2, P3, or however many you have. Okay, so this is going to equal to 2. That's what this should equal to check your answer, because that's what's the total pressure given in the problem. Okay, and that's how you do the partial pressure. Alright, and we'll go over one more example in class concerning stoichiometry, and that'll be all for your final. Good luck.